Zoom. Hello, hi folks. So let me start with my introduction, or maybe with DevDay's introduction first. So DevDay is an informal event for the speakers, not for the speakers, but for everyone in tech industry, so that they get a platform where they can come and contribute and give back to the community. So it's not associated with Sahaj entirely. It's an open event. Everyone can come here and talk about their opinions, interests, and tech in general. So yeah. So today I'm the speaker, and I'll be talking about problems statement that we recently solved in Sahaj. The problem was about building a write-intensive application in which we will get high amount of load from via HTTP calls, and we need to update it.
म्हणजे आपण काय करू?
All right. So let me share my screen and let's get started. Okay. So yeah, people can ask questions whenever they have any questions. So before starting with the slides, let me just go to terminal and let's try out a small experiment. So does everyone know? So I've just written a small command where we say, hey, ls-lh. So does everyone know what this command does? Okay, so let's start. Let me just make another deck, and let's say we do an ls-lh, right? So what does it do? So we have a bunch of things here. So first one is name of the directories or the files, right? And then let's start from left to right, and we'll try to figure out what everything there is, right? So the first one is either it's D or it's a hyphen, right? So what does it mean? And want to, right? So if it's a D there, then it means it's a directory. Otherwise, it's a file, or it can be an executable, any of those things, right? And then we have a bunch of these D, W, X, R, or it's a hyphen, right? So if we club these together, then it basically means that this file is readable, writable, as well as executable for the owner of this, for the user, and this is for the group, and this is for the CH groups. And then we have this number 2. Does anyone know what this means, 2 or these ones? So these are the links. So where this file is being referenced from, these are the links to that. And then we have this root. Does everyone know what this root means? So this is the owner of the file, right? So who owns this file? And there's root again. So why do we have a second root there? Anyone have any guesses? No?
Can you repeat the question?
Right. So yeah, so the question is, over here we have a root, which means that the owner of this file is basically this root, correct? But why do we have root again? What does the second root signify?
It's a group, I guess.
Sorry?
Group.
Correct. So this is the group. And then we have these 6, 77, 165, all these numbers. So what does these mean?
These are permissions, I guess.
No. So the permissions are these one.
Right.
Where we say whether it's readable, writable, and executable or not. And this is something different.
I think is it from executable part?
Sorry, can you speak a bit louder? File size. Yeah. So there's someone on the chat who said it's file size, and that's actually correct. So if the size of file is a bit larger than few blocks, then it's shown in MBs or bits if you provide a H with it. Otherwise, it's shown in kilobits. And then we have this date over here, July 21st, and the time. So what does this time signify? right? So this is modified time. Now the question comes as when, where is this time stored, right? So, we have all of this. So let me just do a small experiment for this, where we will go towards, yeah. Do you want me to make it larger? Okay. Is it better now? Okay. So we are going to deck where we have a bunch of files. If someone is speaking, can you please go on mute if you're not speaking? There's some background noise from your end. Yeah. So we have a bunch of files here, and all of them are around 32 MBs. And what we're going to do now is run a read script on this, right? And which basically does nothing, but it iterates over this directory and it cats all these files towards devnull, right? So there are no write operations whatsoever involved here. Now, when we run this command to execute this script and wait. And then we run IOTop on it, then you can see that reads are being increased, as well as there are some spikes in write. So now the reads have gone away, but there was again a write. So does anyone know why these writes occur?
So I think these files are being sequentially read by the units, and it keeps them in the buffer to make it available easier.
Okay, so so they were read, correct? Then why are there disk writes? I mean, even if it's trying to keep it in the buffer, which is in memory, I believe, then why are the writes increasing? That's the question. Does anyone have any idea or any guesses?
Maybe it's writing them in the memory for the next file, the information for the next file, I guess.
Not really, but so RJN has basically said something on the chat which says file access time is modified, and that's actually correct. So basically, when we if we have multiple files over here, right, and if we do a stat on any of these files, then you will see there's a bunch of information there, which there's access time, modified time, and change time, right? So whenever some user tries to access these files, even if it's a simple cat operation, even then the access time is increased. It goes up. And now if I again run this script again, right, the read script, now we're going to run this again, and we're going to see how basically the interaction between the disk goes now. So what do you guys think will happen now? We've done the same thing, I mean, just 5 minutes ago. So what do you think will happen now? It's the same command we're running. There are no modifications whatsoever we've done to the file system or in the directory. What do you guys think will happen now? It should remain the same, or okay. So let's say we run this now and we say IOTop. Now you will see even the reads are as it is. However, there are a few writes. So initially the write went up, and it might go up again. But basically, even now we try to read the file, right? All of these again 64 kbps around, right? So why is it there? So basically, access time is still being modified, and that's the reason why writes are being changed. But why are there no reads in the IOTop? So for those of you who do not know IOTop basically monitors the input-output operations performed on the disk. So do you guys have any idea why the reads did not go up? And I mean, it's not like a one-off thing. Even if we run it again, and again we say IOTop, even then the writes won't go up. Sorry, the reads won't go up.
Present in the buffer, I guess.
Right. So there's something called buffer cache, which can store these. So initially, it's when the system boots up, it is empty. However, when we read files and these things are being cached. But how do we basically say when is it a good time to use it, or how do we modify it is another question. So we'll be talking about such things in this talk. And let me now start with the slides. Okay. I believe chat and these side hovers are not visible on the stream, right? Okay. So what are we doing? That's the first question over here. And so let me go to this tweet which Yogi posted a couple of months ago when we were building this, when we were trying to solve this problem in our organization called BigO. And what exactly is BigO and why do we have it? So this is a tweet from Yogi which says, hey, the idea is to develop better intuition for how these systems work and the memory and disk performance, the trade-offs which needs to be taken when we decide on which database should we use. And these can only be built when we try to implement it on our own. So in this problem statement, we were given that, hey, you can use any language and libraries, but you cannot use any existing data source or any cache or anything of this sort, right? But all the default libraries and modules are accessible. So how would you build it, and what's the max performance it could support? Now, the problem statement, I believe everyone should have read it. It was in the prerequisite of this talk. And it's a pretty straightforward problem statement where on our server, we are given a machine. I'll talk about the machine in a bit, but the key aspect of it is we have to expose an HTTP server in which you will make a put request, which will contain a probe ID. So there are multiple probes across the server, right? And these put requests will come in and you will give in a probe ID. Sorry? Font, sure. Is it better now?
Yeah.
Okay. Yeah. So a call, simultaneous calls will be made to the server from different probe IDs. So different different probes will make a request to your server, and you have to make an upsert request, right? So if the probe ID is present there, with the then basically update it. Otherwise, use this probe ID and update the data. Okay, and then the other key part of it is you have to always keep the latest copy. You can always forget about the earlier copies. So let's say we get a payload at time X, and then after some time, so X plus 10, we get another request from the same probe ID. Then we can forget about we can delete the earlier one and we can overwrite it with the new data, right? However, so to test and we have to make it persistent. And to test whether it is persistent or not, what they'll do, basically the benchmarking team will do is they will try to send a SIGTERM signal to it. And by sending a SIGTERM signal, it will ensure that the system goes down, right? And then they'll restart the server, and they might even restart the instance to see whether it is persistent in the disk or not. Okay. And there's another condition where we say, hey, the 99% response time for writing a record should not go beyond 200 milliseconds. So our latency is also a concern where we say, hey, 99% should be less than 200 milliseconds. So in the crunch, this is the problem statement. And yeah, for the GET request, there's a 1-to-1 ratio. For every put request within some time, there will be one GET request for it. So yeah, so on a high level, basically there's a benchmarking server and there's a data store server which we need to implement, and there will be calls made to this server, right? So let's now zoom in into the data store server where we'll see what all do we need here. Second, yeah. So what do you guys think should be the components of this data store server? Anyone? So we've established that HTTP calls will be made to our data store server and we need to write it somewhere, right? So what all components will be required in our data store server to, end-to-end process it? Anyone can suggest anything. So there will be multiple components, not just two. So what do you guys think? What should be the components? HTTP server to basically receive the payloads, right? The request, and then send it to someone and do something. So what should be the other components? Anyone? Correct. So to store it in a file or anywhere, we will need a disk, right? So there's a server and there's a disk. So, and in order to basically extract the information out and do our algorithm as to where the file should go to, right? Which directory should it go to and how we structure it, right? For that, we are going to need a service. So yeah, that's what we have next, where we say, hey, there's HTTP server, data store service, and disk. And even on our, okay, sorry, some message broker for async. So it's not actually async communication over here. Yeah. Anyway, so for HTTP server to data store service, I mean, this is what we usually do on our projects as well, right? A request will come in to, and we will have a controller from where we'll pass it to the service. We'll perform some service operations there, some business logic, and then send it to repository, which will then connect to DB and send it to the database. However, over here, we do not have any DB, right? So our data store service has to do the work of DB, where it has to do the business logic, which is to observe and send it to the disk. Now, what interactions do you think, so what other components do you think are required for making the interaction between data store service and the disk? What all will be required? Or yeah, so basically data store service, you could choose any language. So it could be Java, Go, anything, right? And disk is your hardware disk. So how does the interaction happens between your Java or whichever language you choose to the disk is the question.
You require file system component like that interacts directly with the file system.
Right, but so let's say you're using Java, for example, right? Then how does your basically Java application talks to the file system is the next question.
IO calls.
Right, and for IO calls, it is going to require operating system, right?
Yeah.
So essentially, our Java application will interact to OS saying that, hey, I want to either open this file or I want to write into this file and these things. And then again, file system will interact with operating system and in collaboration with kernels in order to interact with drivers and then with disk. So yeah. So we have established till now that, let me just put it up. Yeah, that, hey, data store will talk to OS saying that, hey, I want to open this file or write into this file, which will tell file system and these things. Now, next question is, what is a file system? Sorry, just give it some minutes. Few people have joined in. Yeah. So our application will tell that, hey, we need to save a file, right? So let's say we give a file name and the data which belongs to it, which should belong to that file, which we need to write into that file. So how will it happen? So what, So what is a file system is the next question. What do you guys think? Where does the file system come into this whole picture?
I think it's a representation of the storage in an operating system.
Right. So correct. So basically in disk we have yeah. So or maybe let's start. So basically file system helps us to interact with the disk, right? Like you said, it gives a structure. It provides us a way to deal with the disk, right? So first let's dig deeper into what is a disk. So let's say we have a hard drive or anything, right? So what's inside of a disk? What essentially is a disk? It's a storage machine, right? But how does it store it? Or right, or correct. So that's for right. But even if we go to the lower level, if you're looking at the bottommost level, what are there, or how does it store it? So basically, there are bits, right? At the lowest level, there are supposed to be bits, correct? So there's bits of data. I'm getting an echo. Yeah, if you guys are not speaking, can you guys please go on mute? Yeah, thank you. So yeah, we basically established that in a disk we have bits. At the lowest level, we are going to have bits, right? Now OS or kernel has to talk to disk, correct? Now how will it know, or how will we basically tell that, hey, which bit you need to go to? There has to be some addresses or something around those bits, right? That, hey, I'm sending you this data which I need to write into this file. And then so basically I'm asking about what is the mapping between these two. So we have a disk in which we have different bits, right? And we have an our application, right, which is going to send an command to operating system saying that, hey, this is the file name and this is the data that I want to write. So how do you think this mapping happens?
There are certain pointers which are connected to each other, and there is a certain pointer which is named as the index. Through index we can access the file.
Right. So what's your name? Sorry, Kiran. Okay. So Kiran here is saying that there are certain pointers which will basically point towards
Like a linked list which is connected.
which acts like a linked list, and it goes through each bit, right? But even then, we in a persistent manner, we need to know where. So basically, whenever the system restarts, right? Even then, we'll need to know where everything is mapped. So
There is a certain pointer where the index is present for total file system. Where every pointer means what the pointer connected, there is a specific name.
can we use this, and this will take the input? Is it?
Yes.
Huh? Can you repeat again? Speak. Can you try here? Do a mic test. Try now. Is Kiran's voice audible to everyone on Zoom? Can you say something again?
Hello.
Yeah, so there is some echo, but yeah, it is audible.
There's some echo, but it's audible. Or maybe we can pass this and do that. Just turn it off.
Hello.
Yeah, you.
So actually what I have studied, according to it, there are some pointers, and one pointer means there are many pointers in the database. So some pointer has index related to all the information regarding it. So whenever we want to access some file, we go to the index pointer, we check whatever we have needed, and we go directly to access to that pointer.
So that's true that there has to be a mechanism through which we'll point to everything, right? But if we do it on, so let me try to demonstrate this by an example, right? So let's say we have 1 GB of disk, right? Which means we are going to have 1024 MBs and 1024 KBs and 1024 bytes, right? And then into it, which will give us bits, total number of bits. Now this, if we were to address each and every bit, right? If we were to give address to each and every bit of it, right? Then it would be very it would be a very long number, right? And to store this number, even if it's in a linked list or somewhere in a persistent manner, it will take, again, to store for a single bit, if we have to use these many numbers, right? Assuming that it's in base 10, right? Then that would be a huge number. So to make our lives easier, and by saying our, I mean to make file systems life easier, what we do is we try to basically group these bits into a block. And that's a smallest unit in a file system, which is called a block. So because we cannot basically count on each and every these bits, right? So what we do is we create multiple blocks over the disk and say, okay, and we define a block size, saying that, hey, minimum, the block size is going to be, let's say, on an average, usual systems, it's around 4 KB, which means even if we are writing a file of 1 KB into the system, then it means it is going to occupy 4 KB on the disk, because the smallest block size is 4 KB, right? Now, which means now the other question which comes to our mind is, now how do we decide what should be the block size, right? So what do you guys think?
Simple. There are two types of blocks. One can be variable and one can be fixed. As you said, there are minimum size is 4 KB. That would be the fixed block.
Sorry. Yeah. So Kiran here is saying there are two types of blocks. One is variable and one is fixed size. However, in file systems, at least in ext4 and XFS, the usual file systems, there are only fixed size blocks of any defined number, right? And it stays consistent across all of it, because otherwise, think about it, we'll have to keep in track of which blocks are of which size as well, right? That's an added variable to the equation, right? So to make it easier,
There are fragmentations reduced due to the variable blocking.
right? No, so basically the reason why fragmentation occurs is because like we gave an example, right? We have a block size of 4 KB. However, we are storing files of 1 or 2 KB, right? Now, if this is a one-off case where let's say we have around 1 GB of disk, out of which we are saving, let's say, 8 files of around 100 MB each. So 800 MB is being used pretty good, in a good manner, right? There's not much fragmentation there. However, if and then we, let's say, add only 1 or 2 files which are of 1 or 2 KB, right? In this scenario, it kind of makes sense, right? Because there's not much fragmentation there, right? However, let's say our use case is even in this problem statement, right? We have a use case where the average load size is going to be 4 KB and the maximum is going to be 20 KB, right? But if, let's say, if it were 1 KB, then it wouldn't make sense to use a block size of 4 KB, because then we are essentially wasting our disk, right? So that's the sort of key component of it, to decide what is a block, what should be the block size. There is no silver bullet to it. There is no a straightforward answer to say that, hey, your block size should be this much. It depends on users' need and our workload. So and there's another variable to it, which is, if we have a very small block size, then writing to the disk will take a lot of time, because then performance takes a hit, right? Because essentially there are multiple calls to it, right? So that's the reason why block size should be is dependent upon your workload. So
There are two types of fixed size blocks. Ones are similar. Means if we take 20 KB, then the 4 KB are divided totally by 5 of them. 4 KB, 4 KB, 4 KB, 4 KB. While
Okay.
There is 2 KB.
I think you should, sorry,
8 KB.
let me pass the mic to Kiran. We'll have to start from top.
So the fixed size blocks, there are two type of fixed size blocks. One is if you take the example of 20 KB, then there are 5 blocks of 4 KB, 4 KB, 4 KB, 4 KB. There are self-similar, means they are similar, and while other is 2 KB, 4 KB, 8 KB, and 16 KB, I guess so. Means which total 20, something like that.
Okay. That could be true. I
But then what is the condition then? Which block size we use over here? Means, as you said earlier that we use the fixed size block in this. Then which fixed size block we use? The second one, yeah, first.
Small, yeah, so let me just demonstrate a small command on a normal Rails server. Where we're going to say, hey, just give us the information about this disk of ours. And there we can find that, hey, the block size is around 4096, which is in bytes, which translates to around 4 KB, right? And there are a bunch of other things as well. Now let's forget about it for a minute, okay? So let's take another example. So let's say we are trying to build our own file system, okay? And we have, let's say, so yeah, so far we've established that there's a disk and there are multiple blocks in it, right? Now let's say we're trying to build our own file system and it's around 10 KB, okay? So 10 KB means there are around these many bytes and these many bits, right? Now, we also established that, hey, storing this information directly is a bit hard. So we are going to make blocks of it, correct? So let's say there are, we make, so since it's a small number, so we are only getting around 160 blocks, okay? Assuming that it's of around 512 bytes each block, okay? Now, OS issues a command saying that we want to store this file in the disk, and this is the file name, and this is the basically content of it. It comes to us, and we say, okay, these blocks are free, right? And we say, okay, go ahead and write it there. Now, we do it for multiple files. Eventually, let's say there's a power failure or there's a system restart, right? Now we were just writing it down to ourselves. Whenever a new command came in, we said, okay, this file is there. Go there and update it either or create a new file, correct? Now, let's say there's a restart or there's a power failure and the system tries to recover now. Now what will happen? So let's forget about the power failure scenario right now. Just think about there's a normal restart. Now, since this was all in memory, right? Now the system boots up again. There's a disk in which there's this block of information residing there. But how do we know in which block we have what information?
There are some recovery methods.
No, but so even for a normal restart, we should not use a normal recovery method, right? So when we boot up our system, right? So there should be a way to know that, hey, in which block what information is there. What I'm trying to say is, if we just keep all this in memory, then it won't all this information. So we are file system, right? We need to make sure that, hey, whatever we are trying to write into the disk, we keep this information, right? Now the other thing, what we can do is we should store this information that, hey, this file resides there and it starts from this block, right? And these blocks will be used for this file. We should write this down into our disk, right? Only then when the disk restarts, we will say, hey, go to this file, right? This will give you all file system related information, and we will basically read through it and we will form a directory structure. So let's say the core of any operating system, right? Of any disk, there's slash, right? The root directory. So that's the first information we need to read upon, because based on that we can build everything else. So we basically say, hey, this is the address of this root directory is this block, and from there you will get other blocks, correct? So we need to store this information somewhere. Now, if we store all this meta info, and this is called meta info, right? Because we are just storing information about the files that are inside the disk, right? So if we store this information inside a block, then what will happen? Or basically, what do you guys think? Where should we store it? So we've established that we need to store this information inside the file system somewhere, right? So first question comes, why not just store it into the block, right? We have multiple blocks. So for each file, we'll use a block and store it there. What do you guys think will be a downside of it? or will there be a downside?
For small files, blocks space would be wasted.
Right. Also, even for large files, right? So let's say your meta info is usually of, like we said earlier, block size is configurable on a system where we say, hey, our workload is more and we want, let's say, a block size of 64 MB, right? Because we are only going to have files which are greater than 64 MBs, right? Then in that scenario, if we are also saving the meta info inside a block, then basically to store a few KB worth of info, we are going to waste a few blocks, right? So there should be a different manner in which we store these files. And that's the reason why basically blocks should be, these blocks should be in a different location. And there's another problem with it, which is, or maybe we'll come to it in a bit. So yeah, so basically all these blocks will contain the disk information, which is related to the files. All the file related information will go into the blocks and all the metadata will go into the inodes. So going back to that command that we ran earlier, you will find there are free blocks somewhat, and there are free inodes as well. Now, and again, if we do an ls and stat on any file, yeah, then you will find that there's inode number as well. So this inode number signifies where the information, where the metadata of this basically file resides in. And this is a single number. However, so if we create a new file, right, and we do a ls hyphen or maybe a stat on this new file, then you'll see the block size is 0, right? And when we basically write with it, its size will increase. However, no matter what we write into it, its inode number will remain same because metadata is always supposed to be same, right? Because no matter how big your file gets, your metadata, which is basically these information, right? Access time, modifier time, all of these things. And even the bits that we talked over here, ls-lh, and I was asking you guys, right? Where is this information stored? So all these informations are stored into the inode. Right. So basically, let's say we do this, right? And let's say a stat on dot as well. So there's inode number to it. And all, so basically even so let me stat hyphen, right? So this inode number is 128. So basically the directory of it is, so the root directory contains the inode number 128. Now when we so what do you think should be the metadata info of the root directory or any directory, for example? So access time and all of these are there, and blocks, well, since it's a directory, and so even directories are files in Linux systems. That's why there's a block associated to it. However, it will remain 0, right? The number of blocks associated with it is 0. However, there's a inode number associated to it, right? So this inode number will give you information, will give you info about all the, so basically what happens is when we want to read something, right, it will give us an inode number that, hey, by default, let's say OS issues a command and it says, hey, go to that directory and give me this, or maybe get me that file, right? In order to get to that file, it needs to basically get to that directory first, right? So let's say I want to go to your home. For that, I need to get your address first, right? And first to your town and then to your home, right? So basically, it starts from the first inode, which is this one, to root directory. And then we go to the other one, which basically gives us inodes of all the entries inside of here. So let's say I do an ls-lh on this, right? So all of these will be contained inside that inode. So the inode of 128 will contain a linked list to all these inodes. Not a linked list, but basically a list of all these inodes, saying that, hey, in this single, so this single directory references to all these other files. Does it make sense? Now, there's multiple there are multiple informations in the inode, all basically who can write to this file and all these basically permission information, as well as who is the owner of it, what is the name, and the information which we saw in stat as well. All of this are these are included in the inode. Okay. Now let's talk about the scenario that we were talking about earlier, the power failure one. So let's say now we have inodes, which basically will give us information about directories as well as files inside that directories, right? So let's say OS issues a command saying that, hey, I want to write this file. And basically, let's say it's a huge file, around 150 MB or something, not a huge, but relatively huge. And during that time, while we are writing it, there's a memory, there's a power failure, right? We were writing it, and basically few inodes were created to it saying that, hey, I want to write, inode will only contain meta info, right? So, or to take even a bit more complex example, let's say we are copying a directory from which will have subdirectories, right? Now, when we're copying the subdirectories to other place, it will again create other inodes, right? Now, while this is being done, there's a power failure. So basically, your inode data gets corrupted as well as your block data will get corrupted, right? Now, when you do a, so even in your recovery mechanism, what will happen is it will be very hard for it. Or maybe these recovery mechanisms came in later. I mean, so we are trying to build a file system from scratch, right? So in this scenario, how do you think the system will recover? Is there any way for the system to recover? No, but in this scenario, how, yeah, is, I mean, can you suggest any one in which how? Right. So for log based, we'll have to first create the logs, right? So that's where, let me go to this article. So basically in FAT, FAT32, HFS, all these file systems, this is how things were implemented. Basically there were inodes and blocks, but there were no journals. And yeah, so basically FAT, FAT32, in these there were blocks and inodes, but there were no journals. And then they realized this power failure problem, where if power goes out, then there's a chance that all the data that was being written is lost, as well as there are instances where even the whole disk is corrupted. So how do we recover from that? That was the problem. And then we came up with journal file systems, journal-based file systems. And what happens with, yeah, so in the other late 1990s, such as NTFS uses journaling to solve this problem. So we all understood the problem, right? That, hey, when we're writing to it, whole disk gets corrupted. So what, yeah.
Does inode exist for every block?
No.
No. Okay. In the diagram you showed, it felt like that. That's why.
No. Okay. Sorry. Yeah. So basically, Yadu here asked that whether inode exists for each and every block. So that is not the case, because, I mean, if it did, then this wouldn't make sense. What we had over here, right? If we see over here, we have free blocks and free inodes. If it were to exist, if it
Yeah,
were
I think of inode as a table, like a map, and pointers to the files locations.
Right. So for each file, yeah. So for each file, we will have an inode, but each file can have multiple blocks, right?
Yeah. File have multiple blocks. I am talking about the inode.
Right. So each file have multiple blocks, but each file will only have one inode.
And the blocks, they can be non-continuous, right?
So Yadu here has asked that whether blocks can be non-continuous, and that is true. So there are instances where continuous blocks are not available, right? So it will basically say, hey, from this to this, these blocks are being used, and then these, and all of this information is stored inside the inode.
Just one question. So inode that we see here is the starting point of the file, right? At least that's my understanding.
Which inode?
So inode that you are showing here. So the stats that you did, right?
So
For a
the
file.
so stat for this. So if we do a stat for root directory, then it gives us 128, which is so before it's possible that inodes for basically the file system and other things it might be there, but for the root directory it starts from here. And because from root directory we can essentially get we can get to every other location, right?
Yeah, that's what I am saying. So the 128 is the location
Of the first inode.
From where it starts, and then there are 28 links
Right.
also after that, right?
Right.
So if you check it on a file, that will make more sense.
Right. So
that's the location where it essentially is there.
Right.
Okay.
Yeah. So what were we?
I have a question.
Okay.
Does the inode store all the addresses for each memory block, or are the memory block associated similar to a linked list? So basically, the memory block will tell you where the next memory block is. Or does the inode have all the data saying, okay, if I am storing 5 memory blocks, are all of the 5 in different locations saved in the inode?
So inode will contain a linked list to all the memory blocks that are being used for it. And actually, it also depends on the file system that you're using, because not each file system, but depending on the file system, the implementation might be different. But inodes will be there in pretty much all of them.
So for recovery, can you not just use that information? Like whatever is already written into inode, just try to follow that, right? How many blocks are already written? And
sorry.
The question is, can we not use that information for recovery? If the inode has information like which are the blocks that are already written and for how many blocks the data is written, can we now just follow the right path and see till where it's written and then continue from there?
Right. But what happens when if there's power failure while we're writing to the inode? Exactly. So that's why journaling came in, where we basically write. So journaling is like a or let me not go there. So journaling will basically write everything. So so everything will be written to a journal first. Basically, we'll associate some memory beforehand. So it's like you can think of it like as a pre-staging area, right? Where we write everything there. And when we are sure, like, okay, after every 5 seconds or whatever time we decide on, we can write everything into the disk. So everything essentially will be first written to the journal. And then with time, whatever time we specify, it will be written back to disk.
When you say everything, it means block plus inode.
Everything, yes. Now there are different mechanisms on it as well. Let me go back to this block. Is the font visible? Let me minimize this. Yeah. Cool. So there are 3 modes in which we can use the journal. So this is for ext3 and ext4. So there are 3 modes. First one is journal mode, in which basically metadata is the inodes as well as blocks. All of them are first written to the journal, and hence it is the lowest risk mode, because everything is first written to the journal. And if there's a power failure or anything, then we will read back through the journal and say, okay, this data is corrupted, we can forget about it and continue. And because of this, there's a decrease in performance, right? Because first you have to write to the journal, which is again in disk, and then you have to write, basically put everything to other place, right, in the disk. So when the journal is filled up or when the certain time has passed, we need to write everything into the disk. And if while we are writing to the disk, if there's a power failure or anything, then we can make use of this journal, which you were saying, right? The recovery mechanism. This is the recovery mechanism where we say we make use of this journal and basically correct our data. Exactly. So this is more time consuming, and hence there's a significant decrease in performance, right? And that's why there's another in the default mode in Linux distributions. So this is what I'm trying to explain here, that not every mode is basically applicable on every. So basically, depending on your approach, right, or depending on your need, you have to select your mode. So if you want a very stable system and your performance is not an issue, right, in that mode, journal will make more sense to you. That hey, this is very important information, right? And even in case of power failures, I want this information to be there. In those scenarios, you should use journal. And there's this other mode which is ordered, which is default in most Linux distributions, in which metadata is written to the journal, right? And then the disk info, all the real data is written to the disk. In the first one, both of them, metadata as well as the data, has to be written into the journal. However, in the second one, what they did was write only the metadata into the journal and then write the data into disk. And this is ordered, which means the first metadata has to be committed to the journal, and only after that, basically data can be written to the disk. So that in case of a failure or anything, you will only lose this much data. So everything that resides in your blocks is data, and metadata is your inode spread. Everything that goes inside your inode is metadata. Okay. Now, the third one, which is the least safe, is write back. What happens is it will basically find which one. So depending on the situation, it will say, okay, right now it makes more sense to write the metadata first to the, or maybe the data first to the disk, right? Basically, this is the most performant one, but it is least safe. It will write everything to the journal as well, not everything, but the metadata, but it not in a specific order. In the above one, it is always guaranteed that the data is first metadata is first written to the journal, and only after that, data is written to the file system. Over here, it does not do that. It basically looks at the performance, like which will be more performant.
Can't they do simultaneously while metadata working data?
Yeah, so Kiran here is asking, can't they do it simultaneously? So the problem is IOPS are limited, right? The input-output operations you can perform on disk are limited, and hence we cannot do it simultaneously. I mean, all of this is parallelized. So let's say there are two different files that has to be written. That information can be parallelized, right? However, if for a single file only, you have to write the data as well as metadata, right? But that if there are more number of input-output device, then can we write it simultaneously? So no. Reason being, if you have a disk, right, and you want to write some data to it, then that data has to go into this disk's metadata info as well, right? So basically, if the block resides in this disk, then the inode also has to reside in this disk, right? And hence, you cannot parallelize it depending on how many disks you have. Okay, does it make sense? Any other questions or anything from anyone? No? Okay. So this is most performant one, but the problem with it is if there's a power failure, then you will lose your data and as well as your journal. But across all these three, one thing is guaranteed, that your whole disk, right, will never be corrupt because of a power failure. There might be data loss, but it won't be corrupt. So now coming back to our problem statement. So we've discussed all of this, right? But how does it link to our talk? So then we thought about, okay, which language to use, right? And then we started off with, like if we do a normal Google search, right? Hey, which is the fastest programming language? And well, it starts with 10, and obviously we skipped all of these because who wants the number 10 in these, right? We just want to go to the first one, which is the fastest. It was C, but it is quite complicated to code in, right? So we thought, okay, let's not do this. Then there was C++, where with C++ there are concurrency issues, right? And you have to handle it. Hence, we thought, okay, let's go with the third one, which is Rust. And that did not turn out well. Reason being, we didn't do the research properly, and we basically, okay, and then we did another did in Google search where we say, okay, benchmarking of basically the fastest HTTP server. Sorry?
So when you say you want to find the language.
Sorry.
So when you say you wanted to find a language which is fast, so fast enough means what aspects you are looking for the fast? Is it like CPU intensive fast, or you want to write fast enough to the disk or something?
Okay, so in the problem statement, or basically the problem that we were trying to, sorry, just give me a second. Yeah, so the instances that we were given had only 2 CPUs, right? So obviously it was quite clear to us that, hey, since it's only 2 CPUs, we need to make sure that our language, basically whichever language we use, does not occupy most of it. Like, right, if let's say we use Python, for instance, right, then most of the time will be spent in parsing the data and doing trivial operations. However, it won't as much, it won't spend as much time on the writing stuff. Also, other bit is, even when we say we want to write things on disk, right, that consumes CPU power. Even though CPU is very fast, but even writing to the disk will consume your CPU. Reason being, like we just studied so far, that hey, all of this data, you need to go to the Inode and then get these info. Basically, all of this processing has to be done via your CPU. So hence, there were multiple. So when we say fastest programming language, our main concern was which would be the fastest for the HTTP server, because that's our entry point. It has to be fastest there, right? And hence we ran we used Ntex plus Tokyo, which was marked as the best HTTP server. And the results were around 10,000 requests per second. And this was just HTTP server. There was no data involved or anything. There was just put request being made to the server, and it was replying back with a status of 200. And we were only getting 10,000 or 11,000 requests per second, or maybe even less. So then my teammate, Malik Arjun, had earlier worked on a similar, on last year's Bigo, he had worked on a similar project where they they again had to use an HTTP server, so which was built using Golang. So we used that instead, and the performance it gave was really amazing. So let me increase the font. Let me go to the slideshow. Yeah, it's visible, right, for everyone? Yeah. So this is just the HTTP server we use for Golang, fast HTTP it's called. And with it, we were getting around 123K requests per second, and 99% tile time was around 2 milliseconds. So that's really good, right? And this is with 2-core CPU. So if we go ahead, then basically we did a top. So while these requests were being made, we ran a top on that server, and we saw that, hey, the 99% CPU time is around 199, which means we are getting most out of our CPU, right? And the benchmarking server from where we were running it was, so it had around 8 cores, right? And out of which around 7 are around 50%. So it's trying pretty hard to benchmark our server. So which was a really good sign. And we said, okay, this is good enough for us, right? And then what we thought of is, why not just write the, so basically we are going to get request, right, with probe ID, and we have to write the data into the disk. So rather than using a very complex system, we thought, why not just extract the probe ID out of it and write data directly into disk by using that probe ID as file name. Okay, so we did that, and these are the results with XFS file system. Or maybe let me go back to another question first, which is, how do we decide which file system should we use? So we've talked so much about file system so far. So how do you know which file system should be used? So there are plenty of options out there in the market. There's, like we read, ext4, xfs, zfs.
Really depends upon the requirement of the company.
Correct. It again depends upon your requirement, right? Now, most of these, or that's one way to do it, or yeah. So basically, there's a good article from Reddit over here, which talks about this. Let me zoom in, types of file system. And so now we know the requirement, right? So the requirement is, now you guys are, let me change these, yeah. So now we know the requirement, which is that, hey, there will be around these many requests coming in, right? And we need to write it into the disk simultaneously, right? We are not creating anything complex, just one directory in which we are going to dump all of the data. So which, and on an average file size is going to be around 4 KB. So what do you think should be, I mean, how do we now decide that which file system to use? And this is where we had to do some research. And this is a really nice article that I came across recently, which talks about XFS as well as ext4 file system, which is the default for Rail as well as Ubuntu as well. So most of our files, the file system that we use usually are ext4, right? And these are the questions that you need to keep in mind when you think of which file system you should use. How do you have a large servers and all of these things, right? And there's this interesting bit where it talks about, another way to categorize is that ext file system variants tend to perform better on systems that have limited IO capability. And that was our case, because in our system, we had an IOPS limited to 6,000. And yeah, and the benchmarking we did on the server was around 150, 160 Mbps, right? So hence ext would perform better. However, for anything, if you have large files, right, then XFS tends to perform faster for anything else. So if we go back to our slides, we've done HTTP, and then we basically ran benchmarks for it, right? So on XFS, we did this and we got around 99.2K requests per second, which is sort of good enough, right? And then we went to ext4 to do the same thing. Nothing has changed. Everything remains the same. Same application, the code that we wrote is same for both of them. Just the file system is the only component that has changed. And now here we got around 11.1K requests per second. And there's latency aspect of it as well. But the average request, the 99% request time is around 27 milliseconds over here. And in the above one, it was 175, which is quite bad. So why do you think this difference is there? XFS is like really struggling compared to ext4. The request per second is more, as well as the 99% time is down. Do you guys have any guesses? Sorry? Journaling. Sorry?
Because of two CPU.
Because of two CPUs. That is partly true. So first, Yadu said journaling. So even on XFS, we have journaling, but it's not as advanced at ext4. So that's one reason. And the other core reason is, so why do you think two CPUs will make a difference for ext4, but not for, or maybe for XFS, but not for ext4? So basically, the number of CPUs remain the same in both the scenarios, right? So yeah.
It was a guess only, since you mentioned that ext4 works better with the if we have less IO resources, then ext4 works better. So I took a guess on it.
Right. So that's a really good educated guess. But the next thing is, why do you think ext4 performs better when we have low, basically small files, basically low load? That's the other question, right? So what are the scenarios when we would have low load? That is when we are working with small files. Because when we are working with small files, then what happens is we need to update the metadata continuously, right? So inodes are being updated as well as the blocks are being, and this is where XFS struggles, but ext4 doesn't. And why does that happen? It's because of their implementation. But this is something that we do not, usually know. And while choosing a file system, we do not keep in mind. So hence ext4 worked really well. And then there's something interesting. Let's try it out now. So let me first show you guys that we have a server in which we have around 100 GB worth of things, right? And the file system we are using is ext4. Okay. And now let me go through tmp/data. And we are going to, so do people here are, okay, let me just tell you guys what DD is. So DD basically copies the content of a file. You give it an input file. This IF is the input file where we say, hey, from dev random, random will give you random values. Okay. Or you can even use zeros or anything here, right? We are using random here and saying, hey, write all of this file into file.img. The reason why we're doing it this way is because input file won't have any overhead because this is coming from the CPU, right? So there's no disk operation involved in the input file, and we're only writing to an output file. And we're saying, hey, block size is of 4 KB, which is average. And in our use case as well, it was given that the average payload size will be 4 KB, right? And the count is, sorry, oh man, yeah. And the count is 262144, which means around 1 GB worth of data. So how much time will it take over here, right? And we have another file system over here. Let me increase the font size here as well. And we're going to run this same command over here. Let me just see whether there are any files over here. And there's nothing. So let's run this command. Everything remains same, right? So this is, the machine is same as well. So same as in, these are different instances. This is 189, this is 0, but the type of the machine is same.
Which of the tools?
So this one is XFS, right? Over here. And the first one is ext4, right? Now, if we again, now we're going to run the same command again, first on XFS and then on ext4. So again, we're trying to read from the random file, and then we are overwriting the existing file which resides on the disk, which was file.img. So when we ran it first time, it created a new file, but this time it has to overwrite it. Okay, now how does this perform? And let's do same for the ext bit as well. So in over here, it shows that, hey, it gave the same performance. However, on ext4, we're going to see something very strange of sorts. So the performance has dipped drastically. Over here, we are now getting 68 Mbps, right? Earlier, we got 162 Mbps, but when we are overwriting it, it has dipped to 68 Mbps. Do you guys have any guesses as to why this might have happened? Block size remains same on both of them. Okay, so what's your name? Sorry. Okay, so Devang here is saying that, hey, over here we are overwriting it. So first it might have to, so the file system might have to delete everything that exists already and then have to do it, right? So let's try another experiment, okay? Where we're saying we are going to remove this file, right? Now we don't have any, we don't have that file now. And what we're going to do is we're going to touch it. Touch file.img, okay? Now if we do a stat on it, it contains 0 blocks. There's nothing there, right? Now, again, basically, if your theory is correct, then if we run this, now it should basically do it quickly, right? Let's run it. So it obviously did not complete within 7 seconds, right? So there is still drop in performance. Yeah, again, 68 Mbps. So any more any other guesses? Even everyone on the call. As on why this might have happened.
Maybe it is changing the inode information frequently.
It is changing the inode information frequently. No, but so we're writing to a single file, right? So output file remains the same. So it should only change it once. And if it's only changing it once, then the delta between writing it shouldn't be 10 seconds. So it's not like it is going to spend 10 seconds just to change that that single inode. Why should journal make a difference? So by default, it's ordered mode, right? Right now it's mounted in ordered mode. So only the metadata is written to the journal. Other than that, all the data is written there. So it's not journaling. Actually, the answer to it, even I don't know, but we realized it that, hey, when we try to overwrite it, the performance is low, right? And the number we are getting over here, ext4, update the file of probe with new data was around 11,000, this, right? So we thought, okay, what if we remove these, right? We basically, before writing to the file again, rather than overwriting it, why don't we delete that file and then create a new file? How will that turn out? And there were other optimizations as well. We'll talk about it in a minute. Yeah. So, and then it went up to 19,235 requests per second, which is a huge delta, right? It basically almost doubled. So yeah, that was a really nice finding. And there's another thing to talk here as well. So so I'm talking about the mount options over here, right? No A time, no dir A time, no bad. Let's just focus upon these two first. So what these two options, so initially when this talk started, I showed you guys the access time, right? Basically, when we were reading the files in a directory, it was trying to do some write operations. Using this no A time, it disables that. So let's wrap this up. And yeah, this is my last slide where we talk about the read RPS. So we are in this operation, we are not doing any reads, any writes whatsoever. We are just trying to read everything from the HTTP server. And over here, we got around 50,000 requests per second. And the reason was the buffered cache. Everything was inside the buffered cache, hence everything was really fast. Yeah.
So all your reads were going through the disk, or they were cached in the RAM?
Okay, Amit here has a question. So were all the reads going through the disk, or were they there in the memory? So they were all in the memory, because whenever we perform a read operation on the OS, it basically caches it into the memory, and we can actually tune that parameter in. That's all I had, guys. Do you guys have any questions or anything?
Did you try any more file systems?
We did actually, but the yeah, sorry. So Amit here is asking, did we try any other file systems? And we did. We tried BetterFS, which is ButterFS actually, which is write optimized file system, but it did not really perform that well. And basically, out of all the combinations, ext4 one was the best.
And did you do any like data structure related optimization also while writing to the disk?
Okay, so Amit here has asked whether we did any data structure related optimization while writing to the disk. We did not. It was a really simple, method. It's like a 10 or 15 lines method where we're saying parse the request from the HTTP call and get the probe ID out of it and write it to a file. As simple as that. First remove that file and then write to it a file. That's it.
Hey, how did it compare to actual databases that we use generally? day-to-day use?
Okay, so Karthike has asked a question where he's asking how did it compare to the usual databases, right? So we actually didn't run it on this specific machine. However, on MacBook Pro, which has around 16 cores, Yogi tried it with LevelDB, and it gave around 80K requests per second for reads, which over here is 50. However, the comparison is quite different because it has 16 cores, and the AWS server that we were given, and this is done with 2 cores, and for writes it was 19K for both of them.
So the payload had a variable component to it, right?
Right.
So if the memory, if the payload was more than 4 KB, this would have not worked.
Okay, so Yadu here has asked that payload has a variable structure to it, right? So that's true. It still works because the average is 4. However, if there are more, the average was 4, but the maximum payload size was 20 KB. So even with that, what happens is it basically tries to, even the larger files are created, but for 20 KB, it only has to do like 5 more operations, right? And these are the outliers. On an average, it's only going to be 4 KB. However, if on an average it were, let's say 10 or 15 KB, then it would have made sense to change the block size of the disk to say 10 KB or whatever that number was.
So because you had the block number as the same as the probe number, right?
Correct.
So if it had been more than 1 block, you can actually override some other probe's value.
Right.
Did you manage the caching of the last year?
Okay. I'll talk. I mean, you joined in late, right? So I talked about it earlier. I'll show it to you after this. Any other questions? Anyone?
So it's an SSD.
It is an NVMe SSD for this instance. Yes.
Did you try anything with the IONets? Like, many parallel, what is the limit of the disk to write parallel?
We did not test. We did not test it. But these are concurrent requests, and it's going up to 19,234 requests per second. And these are all simultaneous. And there was one more variable in the question, which was each probe will only come in after 10 seconds. So there won't be any concurrency issues. All right.
Changing the way you store like journaling and write back or whatever, did that help?
Yes. So journaling was quite slow. We got around 8 or if I remember, 4 or 5,000 requests per second with journaling, and then it doubled to 11 or something. And then we implemented this remove first, and then try to write it, and then it again doubled. So it went to around 19K requests per second. All right. Any questions from anyone? All right. That's about it. Thank you guys for joining in. Hope you guys had a good time.
Thanks, Naman.
आता ही अशी बोलते ना, आज मला असं बोल देते पेपर